Hello and welcome to today's e-showcase, Solving Phosphorus and Total Nitrogen Removal Challenges with Advanced Biological Treatment. Before we begin, I would like to thank Evoqua Water Technologies for sponsoring today's event. Today's presenter is David Doobie. David Doobie is the Product Manager for Biological Treatment for Evoqua Water Technologies, a leading provider of water and wastewater treatment solutions. Welcome, David. You may take it from here.
The presentation, and I can turn it back on for Q&A at the end if for anything we have at the end. So with that, let's get started. First, you may have noticed that these slides are Xylem on the bottom. I'm with Legacy Evoqua, or Heritage Evoqua, and Evoqua and Xylem are now one. And this is exciting to be part of a transformative platform. We're going to be able to solve a lot more types of water solutions between the two of us. This just happened within the last couple of months for those who are not aware. And who we are, we're a global water technology company. We provide products and solutions for all sorts of water issues for municipal, industrial, all around the world. With that, so the agenda today, we're going to cover conventional treatment for nitrogen removal and typical modification for enhanced nitrogen, total nitrogen removal. Get into simultaneous nitrification, denitrification, also known as aerated anoxic options for nitrogen removal and enhanced nitrogen removal. Briefly cover phosphorus removal treatment processes and implementation, go over some example plants, and then just touch on some disc aeration novel systems for nutrient removal. So first, when we talk about nitrogen removal, typically many new permits are going to require a total nitrogen removal. And total nitrogen would include ammonia, nitrate, particulate, organic nitrogen, and soluble organic nitrogen. So typically the TKN is going to be ammonia and the organic nitrogens, and then nitrates is sometimes a separate permit requirement. And this is kind of an old slide, so the technology limits may be a little bit better than what this shows here. This is from 2005 from a publication, but it gives the idea, the summary of all the different types of nitrogen that we're trying to remove from the wastewater so that it doesn't affect the streams and lakes that we're discharging into. So nitrification and denitrification are the steps that we use to treat ammonia and organic nitrogen in wastewater, which is predominantly how it comes into the wastewater plant. At the entrance to the wastewater plant, there's typically no nitrates. It's all as organic or as ammonia. And so the organic nitrogen will typically get converted into ammonia through ammonification, but not all of it. And we'll talk about that in a little bit. So the first thing we have to do is treat the ammonia. Ammonia requires ammonia oxidizing bacteria known as nitrifiers, and they thrive in an aerobic environment. They need oxygen and alkalinity to perform the nitrification process. And so they convert ammonia into nitrates. Denitrification is done by heterotrophic bacteria in an anoxic environment. They need carbon, so you have to have some type of food source for them to do the denitrification process, and they use the nitrates then as their oxygen source. So these are typically done in two separate steps in two different tanks, nitrification in an aerobic tank and denitrification in an anoxic or without oxygen tank. So conventional nitrification, denitrification, because we need food for the denitrifiers, we have to have that first before all the food is used up. So typically what we have is an anoxic reactor first. with recycled nitrates from the aerobic reactor. So the nitrates get broken down in here. And then after the anoxic reactor, we have aerobic. That's where the ammonia is converted into nitrates. And then we send back typically 4 times the internal flow rate. So if our influent flow rate is Q, our internal recycle is typically 4Q. We also have the RAS, where we recycle the solids from the clarifiers that are settled. So we get all of our biology returned back to the basin before the clear water goes out. This RAS line, or return activated sludge line, is typically about 100% of the influent, or 1Q. So for all of the discussions here, I'm going to assume that we have a RAS rate of 1Q. So typically no air added in the anoxic reactor and enough oxygen added in the aerobic reactor to break down all of the ammonia plus treat the BOD that's coming into the plant, or biochemical oxygen demand. So the typical process is the modified Lutzik-Ettinger process, or MLE as it's called. And with this process, which is shown on that previous slide, we have the anoxic, then aerobic, and then a clarifier. Our typical TN removal rate for this type of a setup is around 70%, or if we have an influent of about 30, which is typical municipal wastewater, we'll have an effluent of around 10, likely less than that. So that's really governed by our recycle rate and our RAS rate. So the minimum effluent we can get is, because we're converting ammonia in this aerobic tank, any nitrates that get produced have to go out to the clarifier. But if we have 4Q going back to the anoxic tank, that means we only get 1/5 of the flow rate going out the aerobic reactor. And then another portion of it coming back on the RAS. So our total effluent nitrogen, which if we treat all ammonia completely in the aerobic reactor, our total effluent will be only nitrates, and they will be basically Q influent divided by Q influent plus the IR and the RAS rates. And it'll all be as nitrate. I guess I brushed over that a little bit earlier on, but generally when we talk about effluent nitrogen, it's all of the nitrogen forms, kind of like what I said on that one slide. Let's go to the next. So conventional options with post-anoxic and post-aerobic are to further reduce the nitrogen on the effluent. So if we have a total nitrogen limit of less than 5 milligrams per liter, for example, we can't get that with just an MLE process. So we'll have to use something like a post-anoxic and a post-aerobic to break down the nitrates further, and then re-aerate. So in this example, the post-anoxic is going to break down the nitrates, but to do that we need a food source, because as we said at the beginning, denitrification requires a carbon source or a food of some sort. And by the time you get through the aerobic reactor, the aerobic bacteria have consumed all the available BOD. So we have to add some type of carbon source. This can also be done through endogenous respiration as well. And what that means is the bugs that, because there's no more food left, some of the bugs start dying off, and the bugs that are dying off provide food to the denitrifiers. Next slide. So in this example, I put some numbers to it just to help clarify how exactly this process works. So if we have 30 milligrams coming in, 30 milligrams per liter of, assuming it's all ammonia, even though likely it'll be TKN, which is a portion of organic ammonia and ammonia. So if we have 30 coming in, this concentration in the anoxic tank is governed by the flow rate from the recycle, the flow rate from the RAS, and the flow rate from the influent. So the influent in this instant is only 1/6 of the total flow rate, or total flow rate through this anoxic reactor. So the ammonia concentration ends up being 5.4 instead of 30, just because of all the recycle loops. And if we get 90% removal in this tank, we'll get it down to somewhere around 0.6 milligrams per liter of nitrate. Then when we get to the aerobic reactor, we're going to consume all of the ammonia, assuming 90%, that gets us down to 0.5. And because there's no denitrification happening in this reactor, that means that all of the ammonia converted or broken down will be converted to nitrate. So of this 5.4 ammonia that was in here and the 0.6 of nitrates, we end up with 5.4 nitrates here. When we get to the anoxic reactor, then the post-anoxic, we're going to have the same ammonia. No more ammonia is going to be broken down there. We're going to break down this nitrate, and if we get 90% of it, we're down to 0.5. And then when we get to the post-aerobic, we'll get rid of that little bit extra of ammonia, get 90% of that out. That gets us down to 0.05 or rounded up to 0.1 of ammonia, and no more happens with the nitrate. Anything we converted, so that 0.4 milligrams per liter of ammonia that we converted ends up being added to the nitrate that was in the anoxic. So our total effluent ends up being 0.1 milligrams per liter of ammonia and 0.9 of nitrate. So this is all assuming we get about 90% removal in the tanks, and we have 4 Q of IR and 1 Q of RAS. What we didn't touch on here is dissolved organic nitrogen and the particulate organic nitrogen, which you'll get to in a second. And as I said before, we can use endogenous decay as the carbon source in this anoxic reactor if it's sized correctly for that. And if we have the right retention time to support it. So the effluent nitrogen at low levels, organic nitrogen ends up being a large portion of our total nitrogen in our effluent. So if we get down to, I said in the previous slide, 0.9 and 0.1 or thereabouts, we still are going to have the particulate organic nitrogen to worry about and the dissolved organic nitrogen. So particulate organic nitrogen, we can use a filter, either a sand or a disc filter to filter out, but the dissolved organic nitrogen is just going to flow right through. And that's probably the hardest part. This effluent organic nitrogen is really into a couple of different parts. So the particulate organic nitrogen, which I just talked about, which is pieces of solids that contain nitrogen in them. They can be dead cells. They can be non-broken down organic nitrogen that's still in a particle form. That's what the particulate organic nitrogen is. The dissolved organic nitrogen is really two different available forms. One is the bioavailable type of organic nitrogen. So that means something that when this goes to the river, the organisms in the river can use that nitrogen. The recalcitrant effluent dissolved organic nitrogen is a nitrogen that's tied up chemically so that it's not available biologically. So in effect, this recalcitrant effluent dissolved organic nitrogen is not really a factor for the river, but nevertheless, if we're doing a TN, if we have a TN on our permit, we have to count it anyways, even though it technically is not going to hurt the river. There was a study done in 2007 looking at 188 plants in Maryland and Virginia, and they found that this dissolved organic nitrogen, which we were just talking about, that about 35 to 40% of the plants have less than 0.5 dissolved organic nitrogen, which makes it easy enough to meet a relatively low TN permit. But 30% of the plants have over 1.5 dissolved organic nitrogen in their effluent. That's going to make it very difficult to meet a TN of 2 or less, such as Puerto Rico now has to meet an effluent limit of 1.7. So if they have any amount of organic nitrogen in their effluent, they're going to have a very difficult time. And this dissolved organic nitrogen, it can be the result of particular industries you have in your town. So it's not easily controllable. And then we went over all the conventional methods of treating TN. What about SND? I attended a seminar last week about SND and conventional plants, and I want to talk a little bit about how we've done it here at Evoqua for over 40 years. So TN or SND is about adding an aerated anoxic step instead of just anoxic. And so what we're doing is we're adding air in the anoxic stage, but not enough to promote all of the aerobic activity. It's enough to get the nitrifiers going, but not so much that all of the food is consumed. We save some of that food for the aerobic step. So what this ends up doing is we get nitrates removed and denitrification occurring in the aerated anoxic. So when we talked in a standard MLE process, we typically can get to less than 10 with an internal recycle. Well, with an aerated anoxic setup like this, if we don't have the QIR, we can get to less than 10 without having that IR. And so that provides us some pumping benefits. It provides us some tank benefits and some other benefits as well. If we add the internal recycle with an aerated anoxic system, we can get the TN down to 85 to 90% of, we can get an 85 to 90% removal or 10 to 15% remaining of the influent nitrogen. And this is about as good as we can do. It takes the place of having to do a post-anoxic in many instances. If you only have a 5 TN limit, you may not have to do a post-anoxic. So it saves tank volume, having to have an extra tank. So what is aerated anoxic? So that means we're supplying less than 75% of the oxygen demand. So for a single reactor system, it means you're in trouble because you can't get the DO up. But for a system with reactors in series, this is exactly what we want to do in the first reactor. So if our OUR, our oxygen uptake rate is 15 milligrams per liter, we're going to give it something less than 12 milligrams per liter per hour of oxygen. So we're going to limit the oxygen delivery so that we don't use up all of the carbon in that tank. So why do we do this? So first off, the oxygen transfer rate. When we're doing simultaneous nitrification, denitrification, we're doing oxygen delivery at a dissolved oxygen close to or at 0. And when we look at oxygen transfer rate, it's dependent on the difference between our saturation at the surface for dissolved oxygen minus the dissolved oxygen that we're operating the tank at. So if we're operating the tank at a dissolved oxygen of 2 and our saturation is 8, that means that this multiplier is a 6. But if we operate at a dissolved oxygen of 0, then our multiplier for this portion is an 8 instead of a 6. So it provides us a 30% increase in AOR for the same transfer efficiency. So whatever the devices that we're using to deliver air, that's what KLA stands for, we're going to get 30% more oxygen out of it. And so that's a huge benefit for reducing our energy usage at the plant. And this shows just how the chart changes depending on what your operating DO is. So if we're operating at 0 instead of 2, typically that's going to be close to 30% savings. This obviously depends on the saturation temperature or saturation value for the temperature you're operating at. So another benefit is there's less pumping and mixing required for total nitrogen removal. So in the standard MLE process, we have an anoxic tank up front with some type of mixer in it. Well, when we're doing the true SND with a aeration device in the anoxic basin, we don't need to have a separate mixer because the device that's aerating is providing the mixing as well. So we save the cost of that mixer. We also don't have to pump around for the denitrification, so we save the cost of that 4Q recycle pump. If we do internal recycle, we can get to 87% denite with it, and we don't have to have the extra volume for post-anoxic. So here's a diagram with and some example values for if we were doing S&D in with an MLE type process. So if we have aerated anoxic first and then aerobic, we can get the nitrogen down to 5 or less on that very first step, assuming we have about 67% ammonia removal. And when we get into a later example, I think it'll show that we're in the ballpark of this with our typical plants. And we can typically get more than 80% nitrate removal in this first tank, but for this example, I showed 80%. So we're down to 3.1, assuming this 30 gets mixes with the RAS, and we get it down to 5. So the RAS is at 0.5, the influence at 30. You add the two together, that's 35 divided by 2 is just over 15, and multiply by 67%, and that's how we get to 5. And then assuming 80% of the ammonia that was converted, so of that 25 milligrams per liter converted, if we get 80% removed, we'll get it down to 3.1. Then in the aerobic basin, if we get 90% of the treatment of the remaining ammonia, that gets us down to 0.5, and the ammonia that was converted gets added to this 3.1, so our total nitrates then in that tank is 7.6. So that means our effluent is around 8.1 nitrates plus ammonia. So we're less than 10 TN, assuming we have only about 1 milligram per liter of particulate and dissolved organic nitrogen. Will be less than 10 TN without any internal recycle. And for many places that may be sufficient. And here's if we add internal recycle. So if we add the internal recycle, that lowers the concentration of this influent in the aerated anoxic basin just because of the sheer volume. So we have this 30 milligrams per liter only becomes 1/6 of the volume in the aerated anoxic. And if we get 67% removed, that gets us down to 1.7. And then if we have 80% of the nitrates converted, that gets us down to 1.9. So by the time we get to the aerobic, we have much less ammonia to convert and less carry through nitrates. So by the time we get to the aerobic, we're down to 0.2 ammonia and 3.5 of nitrates, which ends up being our effluent then, because whatever's in the aerobic basin is our effluent. These are assuming these are all complete mix reactors. So we're using complete mix type kinetics. So our total effluent then is 3.7 ammonia plus nitrates. If we have 1 milligram per liter of organics, particulate and dissolved organics that we can't control, that gets us to under 5 without a post-anoxic basin. So the disc aeration that Evoqua offers has been introduced in 1968. We will operate oxidation ditches in series. We have a number of reasons why we do it is a round ditch like this. It helps keep it mixed. It's much easier to mix. And with our surface aeration, mixing in aerated anoxic is a key parameter because we want to keep it mixed while also adding air. And the disc aeration that we provide has a high turn-down capability, so it's uniquely suited for providing aerated anoxic in a basin. We don't have to have diffusers with a separate mixer. We can do just the disc aerator. It has excellent turn down, and we get that aerated anoxic at varying levels of flow rates and concentrations. And here's a couple of examples of just a simple aerated anoxic with internal recycle or without. So the first one is a plant we have in Wisconsin where we did a long-range analysis, and we got in the first channel here, the first basin, we're down to less than 10 TKN, which is the ammonia and organic nitrogen in the first channel. And by the time we get to the end, our total is less than 5 if we add these 3 up in our effluent. So we're getting S&D in this first channel. So even if something goes wrong with these aerators in the second or the third channels, we're still well below limits on this first channel. So we have a buffer here built in by doing S&D at the beginning with our total nitrogen. And so if we do have something break down, our chances of having our average TN go above a limit is much less. If we look at this other system, it's a conventional plant with a modified University of Cape Town system. They're doing just anaerobic and anoxic and then aerating. And so by the time they get to the aerobic tanks where they don't have very much distance and time left, they got to convert everything in that, all the ammonia in that tank. So if they don't convert any of this ammonia or only convert a portion because they have some of the equipment down, that ammonia is going to end up in the effluent. And as well, they're going to have some higher nitrates. So it's a much better buffer, and it has a better removal. If you look at the total, the sum here, the nitrates and the TKN here, we're close to 10 here instead of being less than 5. And these are 2 actual operating plants. Here's another one, a plant in Missouri. We got 8 years worth of data to try to quantify how much S&D we're doing. We were getting about 60% nitrification in the first reactor, and basically all of it's denitrified. Our average nitrates in the first channel are only 0.7. And then by the time we get to the end, our TN is about 5. If we do post-anoxic on post-aerobic on a S&D type system, we can get it to even lower values. And with any time we're doing lower values like this, we have to worry about having enough BOD available. And that's actually true no matter what level of nitrates you're trying to get to in your effluent, because we have to have at least 4 to 1, but typically 5 or 6 to 1 BOD to nitrogen to be able to convert all of the nitrogen. So here's a typical example, 1.7 on the or 30 on the influent of ammonia. We get it down to about 1.7 ammonia and 0.4 nitrates in the first tank. By the time we get to the end, we're down to 0.02 of ammonia and 0.4 of nitrates. So we're down to less than a half of ammonia and nitrates. So if we have 1.5 of the other 2, we'd be at 2. A lot of times we can get below the 1.7 that Lake Puerto Rico has now. It's not, but it really is dependent on this organic nitrogen. So if we do phosphorus removal, which is our next topic, we have to have some type of anaerobic tank to convert some of the influent into volatile fatty acid, or the acidification that typically occurs as the first step of anaerobic treatment. So once we get some acids produced, volatile fatty acids produced, then the phosphorus bacteria that are able to use that are going to start absorbing it and releasing some phosphates in the process in that first channel. And so they're going to have an advantage over the other bacteria in that first tank. And we have to remember with phosphorus removal, we have to have a much higher BOD to phosphorus ratio, typically about 45 to 1. And we have to worry about what happens with our sludge, because we don't want to send all of the phosphorus back to the beginning of the plant when we dewater our sludge. So this just has a little diagram of what's occurring. So if you're in an anaerobics basin, the phosphate absorbing organisms will absorb those VFAs and release some phosphates. And they accumulate these organic substances as PHB and PHV, or polyhydroxybutyrate and polyhydroxyvalerate. And then when they get to the aerobic channel, then they start multiplying. They use that food that they absorbed earlier, and they absorb more phosphates and they multiply. And this is how we end up with more phosphorus in the bacteria or in the sludge that we're accumulating in the basin that we can later waste. So here's a typical BNR removal system with a Bardenfold system, which has the anaerobic tank at the front. So similar to what we were talking about before for nitrate removal, but adding anaerobic on the front. And so BOD, ammonia, and phosphate coming in, BOD, ammonia, and nitrates going out. So this is S&D version of the same thing. So a little bit less to do. One other thing to think about too with denite and phosphorus, if you have very low limits and you need to get rid of the particulate nitrogen, particulate organic nitrogen, for example, if your particulate organic nitrogen leaving your process is higher than that 0 to 0.1 or 0.5, you may need a denite filter. You can use one of these types to get rid of that. You can usually get much less than 1 milligram per liter of effluent nitrates with a denite filter. For phosphorus, if you can't get down to the limit you need with the biological process, you have to add either a sand or a disc filter, and then you're going to need some type of alum or ferric, or you can use our COMEG system as another method for helping get down to that really low effluent phosphorus limit. Here's a couple of examples of our S&D type systems with their effluent limits and what they were able to achieve. So this is Salem, Utah, recently installed a couple of years ago. In this particular one, that picture shows they're not even using the outer channel yet, so they're just using it as a two-channel oxidation ditch. Both these channels are in series. There's no internal recycle, but there is an anaerobic basin prior to this basin. So this also shows too what you can do if you have to take a channel down in a oxidation ditch. You can still operate it and you can still get good results. So in this case, it's like one of the first examples I was showing with S&D, we're getting down to about 70% TN removal without any recycle. And this is really with just two basins. Normally we would have three basins in series to be able to get to this, this type of an effluent limit. So they're doing really well. And their anaerobic reactor or their anaerobic basin is helping them get down to 0.24 or better than 95% removal with just a single anaerobic basin in front and the two channel afterwards. And they're not using any chemicals to do this. So if they did have to go below 0.24, then they would have to add an auxiliary system. I think right now their limit is only 1, so they're having no problem meeting their limit. Another one, Johnson Creek, Wisconsin. This was installed a few years ago, a little bit before the Salem, Utah one. So this one is a similar setup. They have all 3 channels in operation right now, and they have an internal recycle. So they're able to get to a bit lower on the TN, but we're actually not even showing it here because they don't have to report it, so they don't measure it. But they do have a very low phosphorus, similar to what we were doing at Salem. Their influent phosphorus right now, this is just based on an average of what they had before the plant went into service. All of this data, by the way, is from the EPA website for the DMRs. So if you have any questions on this, this is where all of this data came from. So if there's any typos, whatever, you can check this site and validate. Another site is Elkton, Maryland. So this one is has a much lower effluent limit. So they have a sand filter after the clarifier to bring their levels even lower. This shows what we can do with a real filter on a system. So in this system, our total nitrogen is the orange one here, and so we're below 1.5 most of the time. We have a couple of excursions above 1 or up above 1.5 here in one place, but over the course of a year and a half, most of the time it was below 1.5. And the phosphorus here is down around 0.2 the majority of the time or less. Another example, Holly Hill, Florida. This one, they have this similar setup with sand filter and disc filters. So they originally had just sand filters. When they did one of their upgrades, they added some disc filters. They run them both in parallel. So they use disc filters for part of the flow and sand filter for part of the flow. Similar results. Their TN is generally below 1.5. They did have one excursion above 2 here, but their phosphorus is down below 0.2 the majority of the time. A couple other systems that we do as well, VLR system and a verticell. So VLR is very similar to our oxidation ditch, except for it's done in a smaller footprint with vertical oriented tanks instead of horizontal oriented tanks. So the liquid moves in a circle vertically rather than horizontally. We can do typically much larger than 5 MGD. We have over 100 installations with this type of a setup. Similar type operating principle where we'll do S&D in the first channel, and aerobic in the last channel, and multiple channels in between depending on the capacity of the plant and the size of the plant. In addition, we have what we call our verticell system. So this is a VLR system. So this type of system seen on the left, but with a fine bubble system added on the end for the final aeration stage. Because by the time you get to the end of the plant, most of the surfactants is consumed, and so the fine bubbles are a bit more efficient there, and it's more cost effective to do the fine bubble at the end than where you're never going to need to turn it down very far. So you can operate at the most efficient point of the diffusers in the last tanks. And here's one example, Springfield, Illinois. We have VLR. This one, though, has primary clarifiers, which typically, if we have a low BOD or low influent BOD like this of only 111, we would recommend against, because we're not going to have enough BOD for nitrification. But in this one, they're doing some unique things with their primary clarifiers to help with the phosphorus removal. And as a result, you can see their phosphorus is down to 0.28. They don't have this low of a permit, but they're very proud of how well they're able to do with using this primary clarifier to help form some of the VFAs needed to get phosphorus removal, even though they don't have a anaerobic tank here at the front. And finally, I guess I just wanted to point out, I've attended many seminars on biological treatment. And I keep hearing more recently more information about S&D. We've been doing S&D since 1980. Chuck Applegate, who was co-author of this paper back in 1980 and who I have a patent with, was talking about S&D back then. We've been doing it for over 40 years. We have lots of experience at it. We know how to apply it and how to make it work for your plant. If you have any questions or comments on how to do that, by all means, let me know. I think that is my last slide. So we got about 7 minutes left for questions. Anybody have any questions?
Perfect. Thank you so much for that great presentation, David. We do have a few questions that have come into the chat pod. I'll read those aloud for you now. Can you route some of the influent BOD, 10% maybe, to the second anoxic reactor to provide the needed carbon?
Well, typically, if it's a second anoxic reactor, you haven't used up all the carbon anyway, so you typically wouldn't need to do that. So I don't know that we have done that, but I'm sure you could. I'm not sure that I see the reason for it, because anoxic means that you're not using up all of the BOD available anyways. So you should have plenty left.
Thank you. How much detention time do you need in the anoxic tank to achieve proper denitrification?
It depends on the nitrates coming around, and it depends on the food available, how long it's going to take, as well as temperature plays a factor as well to some extent. So it really depends on the volume of nitrates coming around with the recycle, as well as the influent food available and how fast it can be utilized. There's not an easy answer to that. There's lots of textbooks that go over that, but there's a lot of factors at play that affect it, so there's no one answer.
Can we achieve removal with only QRAS without QIR and QRAS to be 4XINFF?
Sure, you could, but you're going to be wasting you're going to have to oversize your clarifier so large that it's going to be not cost effective. The reason for doing the QIR is so you don't have to oversize your clarifiers. If you have that much flow going through your clarifier, they're going to be way over. You're going to have to size them so much bigger.
Is the aeration of the anoxic zone intermittent?
If we do aerated anoxic, we do continuous aeration. And that's to provide a continuous environment for S&D type organisms. And we've had studies, there was a study done at University of Wisconsin-Madison where they they observed different species of nitrifiers dominating in that aerated anoxic reactor, and based on having a continuous source of oxygen. And it did show that it was a faster reaction. Go ahead.
Sorry about that, Dave. What would be the DO in the aerated/anoxic MLE?
So if we did aerated anoxic, like what we do now, we do aerated anoxic. Typically, the DO is low enough that it's hard to measure. So we typically will use oxidation reduction potential as a method for determining how much of the oxygen uptake rate is being supplied. But it can be a higher DO depending on the type of aeration device and how easily it is to measure. Sometimes as high as 0.5 to 0.7 DO, depending on where the air is being added, how it's being added, and what device you're using to measure it.
Are systems designed to add lime for alkalinity, or how is insufficient alkalinity addressed?
Just as you said, with adding lime or another carbon source is typical the method to correct for low alkalinity so that nitrification can occur.
We operate in this and target DO of around 0.5 mg/L. Is there a better target, or should be focusing on AOR more than just our DO set point?
Really, the thing to focus on is the OUR. So if your oxygen uptake rate is 15 milligrams per liter, for example, you should know approximately how much you're delivering. You can calculate that with a SOTE test, or you can figure out how much oxygen you're actually delivering, and you want to be somewhere between 1/2 and 3/4 of the oxygen uptake rate. And then you can correlate that with whatever meter you're using to determine if you're in the right ballpark.
Would ORP be better instrumentation?
In some instances, definitely. We've used ORP probes in our oxidation ditches for years, and it's shown to be a good method to control. When you're in the negative ORP range all the time, it works relatively well.
And it looks like we do have time for one more question. Why is RAS 1Q? If SVI is decent, you'll get the solids back at 0.25-0.45Q, or just simplifying to make the math easier?
I was just simplifying to make the math easier. Obviously, you can adjust your RAS depending on conditions at the plant. Some plants will run significantly less if they have a really good SVI, and some plants will run higher. And it also depends on how much you're trying to waste as well. Will have an effect on that.
Thank you so much, David. Did you have any final remarks?
I just want to thank everybody for attending and having the opportunity to present. If anybody has any questions or comments, feel free to email me at this address on the screen, and have a great afternoon.
Perfect, thank you. We will collect all of the questions that we were not able to respond to. I do want to take this time to thank David for a great presentation and to Evoqua for sponsoring today's event. This concludes today's e-showcase. Thank you for joining us. The recording will be available later today, and we will send all registrants an email tomorrow with the link. Please visit our event calendar to sign up for future events.